Hi and welcome to this Transition Year Higher Level Maths Function Revision module video. So this video is part of a series that is helping with the transition from Junior Cert Higher Level Maths to Leaving Cert Higher Level Maths. This is one of two functions videos which will cover everything which you will have already seen at Junior Cert Higher Level. This particular video is going to focus on the basic of functions, which include looking at function terminology, looking at mapping diagrams, the vertical line test of functions, function notation, linear functions, quadratic functions, and exponential functions. So let's take a look at a function. So we have here a domain or an input, and it creates output. A function is a rule that creates an output for a given input. In this example, the function is take an input value, so let's take 2, and multiply it by 3, which gives us 6. So this is a mapping diagram and it represents the function that we've just been talking about. So like I said, a function is a rule that changes the domain value or an input value into a range value. We use the letter X to stand for domain and Y to stand for the range, and this will work as we move forward into seeing them on a coordinate plane, similar to that used when we're dealing with coordinate geometry of the line. So in this case, our function could be written as y equals 3 times x, or f of x is equal to 3x. We'll talk about our function notation in a little more detail in a later slide. So let's look at the terminology in a bit more detail. The domain means the set of inputs. So the domain in this example here to the left is 3, 4, 5, 6, and 8. They're all the inputs, or what we see in the first set in our mapping diagram. The codomain then is the set of all possible outputs. So that's everything we see in the second set of our mapping diagram. That is 0, 1, 2, 7, and 9. The range is then the set of all actual outputs. So notice there on the right hand side of the mapping diagram that the value of 2, although it's there and it could be used, it is not used. So the set of actual outputs are 0, 1, 7, 9. So it is really important that you understand the subtle difference between the codomain, so the possible outputs, versus the range, which is the actual outputs. So let's take a look at a mapping diagram. So here we are given two diagrams. Both of them look quite similar. We have a diagram A and a diagram B. And it's important to note that in this diagram A, that is a function. And this is a function as each element in the domain is mapped to only one element in the range. And that's important. And our focus is on our arrows. So the arrows go one out and it will all land on a value. The second diagram, diagram B, is not a function, and the reason for it is this. Here we have two mappings from one input. So this is not a function as the diamond input is mapped to two different outputs. So let's take an example that might make this a bit clearer. If I put the value of 3 into a formula, I shouldn't sometimes get a 1 and sometimes get a 2. I should only get one specific value. So when I sub it in, I should only get one value out. If I don't, then that is not a function. When we're dealing with with mapping diagrams, like in this case, you're looking out that there is only one arrow coming out of each input. So now let's talk about if the function or relation is not given to us in a mapping diagram. What if we're given instead the picture or the graph? So we have what's called a vertical line test for a function, and it is if any vertical line that is drawn intersects the graph of a relation only once, then it is a function. If this is not true, so if it intersects it more than once, then we have a problem and it is not a function. So let's take this example here. this funny looking squiggle that you maybe don't recognize at this point, and that's fine, but all we need to see is it a function? And the answer is yes, because there's no vertical line I can draw that will touch the graph more than once. This example here, this is not a function, and the reason it is not a function is because when I draw this vertical line, it touches or intersects the graph twice, so it fails the vertical line test. This is also not a function because no matter what line I draw, I can see that there are some that will intersect this relation or graph twice. Therefore, it is not a function. Now let's talk a little bit about function notation. So the most commonly used function notation is this here. This is pronounced f of x is equal to 2x plus 1. F is the function name. X there is our input, and 2x plus 1 is our output, or the rule for an output. So if I told you x was 1, we could then use that rule to calculate our output. Some pieces to note. F of x, this is pronounced f of x. It's important to get used to saying that correctly because it is not f by x, or it is not multiplication, it is something very specific. So do get in the habit of saying f of x. F of 2 then will be f bracket 2, and f of x is another way to say y. So y is what they will all be. So y, we think of it as our x and our y axis. But f is more specific to the name. So the analogy I would give is the idea that if you have girls, that would be equivalent to the y, but you wouldn't go around going girl, girl, girl. It's much easier to work with people if they have something that identifies them specifically, and that to us is our name. So I would say Mary, Anne, and so on. So F is the name. It is specifically the name. All of these functions, f of x, it could be g of x, it could be h of x, that's all names, but they are all y's. In the case like all of these are girls. So just be really clear about that. If we want to work with a few functions, we often give them specific names like f of x, g of x, h of x, but they are all a y value. Another type of function notation you'll see is this, and this is f is the function such that x is mapped to 2x plus 1. Now, at junior cert higher level, you will see this in a form like this, but my suggestion would be to always rewrite it as our above f of x. If you were wondering why we even have this, this becomes a much more useful notation as we move into Leaving Cert higher level. So just like before, f is our function name, x is our input, and 2x plus 1 is our output. So my advice to you is if you see something like this, that you come along and rewrite it as f of x equals 2x plus 1, because this is the most useful format for us, and this is going to be the one that will help us work through the questions. So let's work through a question. They've told us that the function f of x is equal to 3x plus 5. Find the value of f of 7. So we knew what f of x was. So what has happened is the x has changed to 7. So everywhere we have an x, we're substituting in 7. So we get 21 plus 5, and that gives me 26. Then they've asked us for f of k. In the exact same way, instead of x, they've given us k. So everywhere we have had an x, we sub in k. And that's as much as we can do. We should know at this point that it is not possible to add a 3k plus 5. So using your answer to be or otherwise, find a value of k for which f of k equals k. So we know f of k is 3k plus 5, and that should equal k. So this is a linear equation. Let's subtract a k from both sides. Let's subtract a 5 from both sides, and we get 2k is equal to minus 5. Divide both sides by 2, and we get k is equal to minus 5 over 2, or if you prefer, minus 2.5. So it is really important that you recognize whatever value they give you in the bracket, that is our input, and we put that exactly where the x had been. So let's talk about linear functions. So linear functions are very much linked to what you would have already covered in coordinate geometry of the line. If you've not already done so, it might be a good idea to go back over the coordinate geometry of the line video and to revise everything got to do with lines. So just like our coordinate geometry of the line, linear functions are written in the form y equals mx plus c. However, instead of y, because we're in functions, they may call that f of x. What doesn't change is that the m will stand for our slope and the c is the y-intercept, or where the line crosses the y-axis. Remember about our slopes, we have a positive slope, which is read from left to right and it works up. Negative slope, again you're reading from left to right and it goes down. A horizontal line has a slope of 0. Just a reminder that slope is a measure of how slanty a line is. So here there is no slope. And a vertical line has what we call an undefined slope. And we'll talk about that a little bit more detail as we work in trigonometry. So here is a question that asks us to draw the following function in the domain minus 2 is less than or equal to x is less than or equal to 2, where x is an element of OR. And the function is y is equal to x minus 1. So one thing to notice here is that this is linear. And the reason I say to notice this is because if you can notice that it's linear, it is going to make your life a lot easier. The reason for this is simple. If you can remember back to your geometry, when I want to draw a straight line, all that is required is 2 points. So when I draw a function that's not linear, and we're going to see 2 more examples of those, I will always want to do as many points as possible so I can effectively join the dots and see what the graph looks like. But with a linear, all I need to do is to draw 2 points and use my ruler to connect them. So because I've noticed that this is linear, and the reason I know that this is linear is it looks like y equals mx plus c, or in particular, this x is to the power of 1. Okay, and that's how we recognize a linear, because it is an x on its own, or you can think of it as an x to the power of 1. So I'm going to create my table, but I'm only going to work with 2 points, and I'm going to work with both endpoints. So when x equals minus 2, so we're going to start off with our x values here. So let's take when x is minus 2 and x is 2. Our function is y equals x minus 1. So y is equal to minus 2 minus 1. That will give me my y value here, which is minus 3. And the last thing I'm going to write is my point. So I get minus 2 minus 3. Similarly here, y is equal to x, which is 2 minus 1, which gives me a plus 1, which gives me 2, 1. So I go to my graph and I fill these in. So I get minus 2 minus 3, which is here, and I get 2, 1, which is here, and this will allow me to then use my ruler to connect it. So I'm going to try use my ruler. Sometimes my screen doesn't like when I put my ruler down. Now, not great because I'm trying to work with my screen, but this is what we should get here. So we have y equals x minus 1. So if we hadn't noticed that that was a linear function, we could have done every value from the domain. So we could have done the point here, could have done our point here, our point here, and our point here, but that would have been more work than we needed to do. So remember, you want to work as efficiently as possible. Noticing that this is linear makes your life a lot easier. Now let's talk about quadratic functions. So quadratic is something which you would have seen a huge amount of in algebra, and it's really important that you understand how all the stuff that we've done in algebra also then links into the function space. So this graph I have on the left is a positive quadratic, and positive will mean that the a value is greater than 0, or the leading coefficient is greater than 0, or positive when I'm dealing with ax squared plus bx plus c. So basically what I'm saying is that this piece here, that is going to be positive for that graph. On the right hand side then, this graph is a negative quadratic, so a will be less than 0 or a will be negative, or the leading coefficient will be negative. So in this case my a here will be negative. That is how we can identify from the actual function themselves and from the graph. A great way to think of this is that positive people smile, so our positive graph looks like a smiley face, and negative people frown, so our negative there looks like a frowny face. So be aware of how you can identify both the function graphs and from the basically the function notation that it's given, how we would figure out if it's positive or negative. So these 2 points here are called our roots, and we have the equivalent here on the negative side as well. The roots are where the graph itself cuts the x-axis. So when we were dealing with coordinate geometry of the line, we didn't refer to it as our root, we called it our x-intercept. We're going to use the term root now as we work through quadratics because it is a better use, it's a better word to use, and you'll see it a lot more often as we work through questions. We then have what's called the y-intercept. Here it is in blue on both graphs. This is where the graph cuts the y-axis. So we saw that in coordinate geometry of the line, and we would have known that to get the y-intercept we would have let x equal 0. The third thing that you might be able to see here is in yellow, and on the positive graph we have what's called a minimum turning point. On the negative graph we have what's called a maximum turning point. Now let's work with an example of graphing a quadratic function. So draw this function y is equal to 2 minus x squared in the domain minus 2 is less than or equal to x is less than or equal to 2. So just to take a look at this, this is a negative quadratic. So straight away I know when I draw it, it's going to be this frowny face here. How I know it's negative is I look at the x squared part and I see that the leading coefficient is negative. So one way to think of this is which thing has the biggest power. So it's x to the power of 2, so it has the big power. So the one that has all the power, when that is negative, the whole thing is negative. When that is positive, the whole thing is positive. So we're going to work with our little table and see. So I've already filled in my table. The first column is my x, which goes between minus 2 and 2, and that's coming from my domain here. I then fill in my actual function itself, which is y is equal to 2 minus x squared. Remember to put all those values in as bracket squared. That gives me a y value, and then it gives me a point. So I'm going to go straight to plotting my point. So I get a minus 2 minus 2. I have a minus 1, 1. I have a 0, 2. I have a 1, 1. And I have 2 minus 2. So I want to draw this. Again, please bear with me. I'm on the computer and it's quite hard to draw. And we get something like this. And I label this y is equal to 2 minus x squared. And this does look like the negative quadratic that I predicted it looked like. Do note that when we're drawing a quadratic function, you cannot, under any circumstances, use your ruler. This is a curve. Every piece of it should be very curved, and if they think in an exam that you've used any kind of ruler or it's too flat, you will be docked marks. So you want this lovely curve. It doesn't have to be perfect. Mine is definitely not perfect here, but it's the best I can do on the computer. You could probably do a lot better on your page, but you're not looking for perfection. We're just looking for that lovely curve. So now, let's talk about finding the roots of a quadratic function. So we talked about the roots being these 2 points here, and they're equivalent to what we would have called the x-intercepts as we worked with the equation of the line in coordinate geometry. So here they've asked us to find f of x equals 0. So remember, f of x is another way to say y equals 0. And just like when we were in coordinate geometry of the line, if we let y equal 0, we got the x-intercept. So my f of x is 2x squared plus x minus 6, and I want that equal to 0. At this point, you might go, oh, this looks familiar to me. And the reason it probably looks familiar is because now what we have is a quadratic equation. And what we're being asked is to solve it. So anytime we're solving a quadratic equation in algebra, we're doing the exact same thing as finding the roots of a quadratic function in the function space. It is the exact same question, just asked in a different way. So we have two methods of doing this. Since they've given us no indication about how to give our answer and in what kind of form, we can assume that both are valid. So the first way that we can do is to work using factorization. The second is by using the quadratic formula or minus b formula. I'm going to work with factorization, so I'm going to use the guide number method. So the guide number in this case is the first multiplied by the last, which is 2 by minus 6. Which is minus 12. So that is my guide number. And I need to factorize that such that I get a plus 1 when I add them together. So minus means different signs. So one is going to be positive and one is going to be negative. So if I say 4 and 3, where 4 is a plus and 3 is a minus, that will add up and give me a plus 1, which is what I'm looking for. Remember, the purpose of this is I'm trying to separate this plus x into two pieces so I can do grouping. So 2x squared plus 4x minus 3x minus 6 equals 0. At this point, I would suggest to you to double check, does plus 4x minus 3x, does that give me plus x? A lot of times students making very silly mistakes with signs. Please double check at that point. Everything now is fine. Take out a 2x, which is common. I'm left with x plus 2 minus 3, and I'm left with an x plus 2. At this point, my check is, are my brackets the same? They are. That means I'm going on the right track. So I get 2x minus 3, x plus 2 equals 0. So now I'm going to let each factor equal 0. So I get 2x minus 3 equals 0, which gives me 2x equals 3 as I add 3 to both sides, and x equals 3 over 2, or if you prefer, you can write that as 1.5. Then I get x plus 2 equals 0, and I'm going to subtract a 2 from both sides, and I get x equals minus 2. So what we have here is the roots, and in this case there's my minus 2, and here's my 1.5, and this is the function f of x is equal to 2x squared plus x minus 6. So it's so important that you see the connection between solving quadratics, which you've been doing probably since second year, and working with the quadratic functions, which is possibly a little bit newer to you. So now let's look at an example where we're still working with the quadratic function, but we're working with it in a slightly more challenging way. So part of the graph of the function y is equal to x squared plus ax plus b, where a and b are elements of z, which stands for our integers, which means they're positive or negative whole numbers, is shown below. The points R and S are on the curve. Use the given points to form two equations in A and B. So this leads us to a very important fact, which we've already seen in coordinate geometry of the line, and that is, if a point exists on a line or on a curve or any type of function, we can substitute in that point for x and y into the equation and it will work, as in the left hand side will equal the right hand side. So let's work first of all with the point R. So the point R is 2, 3. This gives me the x part and the y part. The function itself is given as y equals x squared plus ax plus b, which gives us, instead of y, we're saying 3 equals x squared, so 2 squared, plus a times 2 plus b. So we can clean that up a little bit. So we get 3 is equal to 4 plus 2a plus b, and cleaning it up just a little bit more, we get 2a plus b is equal to minus 1. So subtracting a 4 from both sides. And that gives us equation 1. We can do the same thing again for our second point, which is s, and that s is minus 5 minus 4, which again is our x and our y. Our equation is y, which is minus 4, is equal to x squared, so minus 5 squared, plus a times minus 5 plus b. And working that through, it cleans up to minus 5a plus b is equal to minus 29. So when we work through this, minus 5 squared will give us 25, and we would subtract that from both sides. So that gives us our second equation in A and B. Now we've been asked to solve your equations to find the values of A and B. I have two equations and two unknowns, so we're using simultaneous equations. We can use any method that we have, and we've gone through some methods in the algebra module to do this. The most straightforward and likely method that people will go to is elimination, so we get one of our values to eliminate. The easiest thing to eliminate here is our b's, and we can do this by multiplying the bottom line by minus 1. So we get the top line is unchanged, 2a plus b equals minus 1. Multiplying that across, I get 5a minus b equals 29. The b's end up cancelling, so plus b minus b is effectively 0. And working this, I get 7a is equal to 28. Dividing both sides by 7 will give us a equals 4. We now go back to either equation. I'm going to take equation 1, which is 2a plus b equals minus 1, and we're going to sub a. Instead of a, we're going to sub in 4, so 2 times 4 plus b equals minus 1. So that gives me 8 plus b equals minus 1. Subtract an 8 from both sides, and we get b is equal to minus 1 minus 8. B is equal to minus 9. So what we actually have here is the quadratic equation y equals x squared plus 4x minus 9. And if you want to just take a quick look at the graph and see, does that make sense? Well, the first thing I would look at is that constant, that minus 9 is the y-intercept, and at least it's in the right part of the graph. We don't have any other information we can work out at this point, but that's enough for me to say, well, look, there's nothing obviously wrong. So now we extend this, and it asks us to write down the coordinates of the point where the curve crosses the y-axis. So we've just talked about this. Just to remind you, y is equal to x squared plus 4x minus 9. If I want to find where it crosses the y-axis, or the y-intercept, our rule is we let x equal 0. The same rule that we have when we're dealing with coordinate geometry of the line. So y is equal to 0 squared plus 4 times 0 minus 9. So y is equal to minus 9. But that's not enough. They want the coordinates of the point. So we write this as 0 minus 9. You could have also just looked at the constant part, the bit without the x, and that would have given us the point that we're looking for, which is here. So that point here is 0 minus 9. The last part of this is by solving an equation, find the points where the curve crosses the x-axis. So here what we're looking for are the roots of the quadratic, or what we would have called these when we were dealing with the line is the x-intercepts. So to do this, we let y equal 0, which gives us x squared plus 4x minus 9 equals 0. So effectively we're solving this quadratic to find two values of x. So notice that the question said, give each answer correct to one decimal place. If you can remember back when we were working through the algebra module, what we said was if there was ever a quadratic that gave you a hint such as correct to so many decimal places or insert form, it was important to note that this was a big hint to you, telling you that you had to use the quadratic formula. So the quadratic formula is also known as the minus b formula, and it's found on page 20 of your log tables. So the minus b formula is x equals minus b plus or minus square root of b squared minus 4ac all over 2a, where we're given ax squared plus bx plus c. So we can work from this saying a is the coefficient of the x squared, which is 1, b is the coefficient of x, which is 4, and c is the constant, which is minus 9. So x is equal to minus 4 plus or minus square root 4 squared minus 4 times 1 times minus 9 all over 2 times 1. Cleaning that up, we get x equals minus 4 plus or minus square root 16 minus 4 times minus 9 is plus 36 all over 2. And then we get x is equal to minus 4 plus or minus square root of 52 all over 2. We can simplify minus 4 plus or minus, and this simplifies down to 2 root 13 all over 2, and this is x equals minus 2 plus or minus the square root of 13. So if you're asked in third form, that's our two answers. We can simplify this now, taking the plus and taking the minus, and then we can work out our two answers correct to one decimal place. So we get our two answers as x equals 1.6 and x equals minus 5.6, both correct to one decimal place. So now let's talk for a second about exponential functions. Exponential means that we have something written with a power, and our variable or our input in this case is in the power. So if you can think back to when we were working with our indices, there was three things that we used to call the power. It was the index, it was the power, or it was the exponent. So the word exponential comes from the idea of there being an exponent. So one thing to recognize is exponential functions start off quite flat and become very steep very quickly, or the opposite is true. They start off very steep and become very flat. Look at our graph here of f of x, 2 to the power of x. So just like in our indices, we have the base, which is the big number, and we have a power. Note that there could be some number put in front of the base, but in the most cases we're going to see that as simply 1. So let's take an example of an exponential function that we've been asked to draw in the domain minus 2 is to 2. So straight away we can recognize this as an exponential because the x, or that input or that variable, is part of the power. So if you didn't realize that was an exponential, that would not matter at all, because simply doing out our table and plotting our points, we should be able to draw the exponential function. So let's work with our table. So our first column is our input, that's our x's from minus 2 to 2. We then work the actual function itself. We sub in our value for x, or our input, we get our value for y, and we get our point. So now we have a series of points here. Let's work with this and let's see what the graph looks like. So we have minus 2 and 0.25, which is about here. It's a quarter. We have minus 1, 0.5. Oh, that first point didn't come out. So let's see. Minus 2, 0.25, minus 1, 0.5, 0, 1. We then had 1, 2. We then had 2, 4. So what we get is this graph that starts going up very, very quickly like this, and it is y is equal to 2 to the power of x. Don't forget to label it each time we work. Again, like with the quadratics, it's important that you don't use a ruler when you're doing this, that this should be very much a curve.